Today I am going to talk on mineral beneficiation. As in the previous lecture on introduction to metal extraction, I have said that metal grade of the ore is very important. The technique of metal extraction, that is pyrometallurgy or hydrometallurgy, they require a grade of ore or a metal grade of ore which should be sufficiently high, so that the waste production is as minimum as possible. Therefore, in all extraction processes, whether it is pyrometallurgy or hydrometallurgy, it is necessary to increase grade of the ore, or rather metal grade of the ore. Why? Because of two benefits. If you increase the metal grade of the ore, first, to increase the metal yield, and the associated second advantage is to reduce the amount of gangue, Third advantage by increasing the metal grade of the ore is to decrease the thermal energy requirement. In order to separate metal from gangue in pyrometallurgical technique, because as I said, the pyro means temperature. So, the separation of metal from gangue occurs at high temperature. So, the third benefit is to decrease the thermal energy requirement, and the fourth benefit is that you recall another route of metal extraction was hydrometallurgy, where a large amount of aqueous solution is needed. So, by increasing the grade of the metal, by increasing the metal grade of the ore, you will be able to decrease the aqueous solution requirement, in hydromet route. So, these are the some of the benefits by increasing the metal grade of the ore. Now, the question comes how to increase the metal grade of the ore. So, the first step, whether it is pyrometallurgical extraction or hydrometallurgical extraction, of the first step is called mineral beneficiation. The objective of this step is to increase the metal grade of the ore, that we are very clear we have to increase the metal grade of the ore. Now, this mineral processing technique, it requires two things. One is the liberation of the mineral, and second is the concentration of the mineral. So, there are two steps are required. In mineral processing. One is called liberation of mineral. Now, by liberation of mineral, I mean if you take an ore from the natural reserve and try to observe under the microscope, then you will find the valuable mineral is distributed within the grain, across the grain in a very, very small amount. So, if you want to increase the metal grade of the ore, then you have to liberate the mineral from that matrix of the gangue. How can you do that? How can you liberate the mineral? In that, you crush and ground it. Depending on the valuable mineral which is present in the ore, its size and shape, you plan your size reduction technology such that the liberation of valuable mineral is achieved. So, in fact, liberation of mineral, it requires the so called size reduction technology. Size reduction technologies. What we are talking of? To create a state from the lumpy ore which is in hand to a state where we can obtain the separation of valuable mineral. We are talking of purely physical separation, and that can only be achieved once that particular lump of the ore, you reduce its size so that the valuable mineral is set free, and later on by the so called concentration technologies, the concentration technologies can be used to separate valuable mineral from the ore matrix. So, what will I do now? I will take both these steps in brief, because the objective of the course is not to go into detail of these processes. Towards the end, I will give you the reference where you can read if you are interested in the detail. Here I am going to give you those details which are required to develop the material balance in case of mineral processing, because that is the objective of the course. So, I will give in short what is required, so that while applying the concept of this liberation or concentration technologies to solve the problems on material balance, that is the objective. So, in that perspective, I am going to give you the brief details of both these technologies. So, let me take first of all the liberation. We are talking of liberation of valuable mineral. That is what our objective is. Now, this is achieved. One, crushing is the first stage. What you do? You take the lump ore from the natural reserves. Because of its huge size, it is being crushed to some of the intermediate size. So, the first step is crushing, and crushing is followed by screening, so that you can remove the oversize from the undersize. Undersize means the product which is acceptable for further size reduction technologies. So, crushing, which is followed by screening, and in the screening you have oversize and you have undersize. One which is passing through a screen, you call it to undersize, and one which retains on the screen, you call it a oversize, and the oversize can be sent further back into the crusher, whereas the undersize is sent back to further size reduction operation. Now, you may argue, sir, while in the crushing we may have attained the mineral in its fully liberated state. No, it is not possible because of the size. So, then it is ground further. So, the next stage in case of liberation, that is called the grinding. Or sometimes this is also called milling operation. This is also called milling operation, and in the milling operation the feed for milling operation is undersize from crushing operation, from crushing, that is the feed for the so called milling. Now, let us see how the milling is attained. Now, milling in fact is a size reduction technology where the feed is ground to a state of fully liberation of particles. So, this milling is in fact what is being done. The feed is taken into a cylindrical type of vessel which rotates at a particular speed, and the size reduction of the feed occurs by the medium. So, in fact, in the milling, in short, force for size reduction is applied through a medium. Now, medium, that could be balls of different sizes, they are spherical balls of different sizes, then there could be rods. So, these are the medium, they are used to ground the feed from the crusher so as to get the valuable mineral for further concentrating operation. So, according to the vessel which is being used for milling purpose, the milling is named according to this. So, one is called ball mill. In the ball mill, the feed is rotated in a cylindrical vessel at a particular speed, and the medium of grinding, they are spherical balls. That is why this is called a ball mill. Now, here speed of the mill is important. You cannot run the vessel too high a speed or too low a speed, the details you see in any book. So, one is the ball mill, because their spherical balls are used as a medium for grinding. Another is called rod mill. Another is called rod mill. In the rod mill, instead of spherical balls, straight rods are being used to mill the feed. Now, since the objective of milling is to get the valuable mineral in its liberated state. So, one has to go to a very fine size. I mean that fine size where you are sure that now the mineral is completely liberated from the matrix of the ore, because in the ore valuable mineral and gangue, they are intimately mixed. So, you have to separate it by reducing its size. So, that is what the objective of this ball milling or rod milling. So, because of too much amount of fines is produced, and because of what should I say, so a lot of pollution and so on. So, milling, particularly ball milling, say milling is done under wet condition. However, it depends upon the size up to which you want to ground the product, but mostly milling is done under wet condition. The objective is to reduce the amount of pollution. So, here in this, that is also called as a wet milling. One is a dry milling, another is a wet milling. In the dry milling, no water is used. In the wet milling, water is used. So, here for wet milling, material balance is important. Material balance is important. Why it is important? First of all, to know what is the amount of water in a milling circuit. I will tell you what is circuit. In a milling circuit, and second is that percent solid in slurry, percent solids in slurry. A slurry is a mixture of solid and water, as I have discussed this when I was lecturing on stoichiometry. Now, both this information, why do you want it? You want to transport this material from one location to another location. Say in the circuit also, you have a crusher, followed by screening, followed by ball mill, followed by again a sort of a separation device, then you undersize, you oversize, then you want to transport from one operation to another operation, you require a huge amount of pump, because you are not dealing with few kg of the material, you are dealing with the few hundred tons of material per day. So, you require what should be the capacity of the pump to transport the water, or moreover what should be the capacity of the pump to transport a slurry, because a slurry is a mixture of solid and water. So, you should know what is the percentage of solid in the water, so that you can decide on the pump, what type of pump you require to transfer the slurry, which is a mixture of solid and water. So, for all these things are important. And another thing, say for wet milling, also it is important water upon solid ratio. Water upon solid ratio is important. As you all know that I have said water plus percent solid, this mixture is called a slurry. Sometimes you may also call is a pulp. Both names they convey the same thing, slurry or pulp. So, here what is important is that the viscosity of slurry is important. Viscosity of slurry is important. Why it is important? Can you think of? For that you have to think what determines viscosity. Viscosity determines the flowability of the mixture that you have formed. In the grinding operation, since the mill is rotating at a particular speed, so the slurry should also be easily move into the vessel. For that the viscosity is important, and for that percent solid in the slurry is an important issue. Now, two things can occur: too dilute a slurry, or you have too concentrated a slurry. Too concentrate a slurry. Now, if you have too dilute a slurry, that means what? The percent solid is very less, the amount of solid is less, you have put the medium according to your calculation. Because solid is less, now the medium will interact with each other. So, too dilute a slurry will cause wear of the medium, that is very important. If you have too concentrated slurry, that means your percentage of solid is very high. You thought of, well, let me mix more amount of percent solid, and you do not know what is the percent solid in your slurry, and you have made too concentrated slurry. What will it do? Slurry has to move, its viscosity has become very high, so it will be very difficult to move. So, in that case, too concentrated slurry will cause a so called cushioning effect, will cause a sort of cushioning effect, whereas 2 diluted slurry will lead to wear of the medium, which is spherical balls in case of ball mill. So, these are the hazards of not having an optimum percent solid and percentage solid in the slurry, and for that it is important to calculate what is the percentage of solid in a slurry in order to come to an optimum composition of the slurry, or you can call the optimum density of the slurry. Now, as you recall in my stoichiometry lecture, I have given you the formula. I will just write over here straight away, say percent solid in a slurry, percent solid in a slurry, that will be equal to, if you recall this formula, I am writing once again, 100 into rho s upon rho m minus 1000 divided by rho m into rho s minus 1000. This is all density, where rho s is the density of solid, rho m density of slurry, 1000 is coming because you have mixed solid in water, and water has a density of 1000 kilogram per meter cube. So, just an illustration, if I take for example, a solid which has a density rho s equal to 3000 kilogram per meter cube. Now, you have to substitute the value all in kilogram per meter cube, because I have used the density of water in kilogram per meter cube. And let us take, we want to make the density of slurry as 1500 kilogram per meter cube. Then I can find out by putting both these values into the formula on percent solids. So, I can know now the percent solids in a slurry, that will be equal to, you can just calculate it, is 50%. You can substitute those values, it is very simple, just substitute the values and you will get the answer. Now, what will I do with the percent solid? Now, I can use the percent solid to find out the mass flow rate of the slurry. So, ultimately mass flow rate of the slurry, that will be volumetric flow rate of the slurry into density of the slurry into percent solid divided by 100. And now, if I take F, which is the volumetric flow rate of the slurry, as 0.8 meter cube per hour, rho m is the density of slurry. So, if I substitute, I get m equal to 600 kg per hour, that is the mass flow rate of solid in the slurry. So, I mean these are the say important calculations that can be performed while performing a material balance to know what is the percentage solid and so on. Now, as I have said, these flow in a circuit. Now, what is a circuit? Now, suppose if I want to make a milling circuit, let me make a milling circuit. Now, very often in the milling circuit, the feed is fed into the rod mill, then it goes for the separation, then you have undersize, oversize and connected with the ball mill. So, a milling circuit, if it comprises of rod mill, hydrocyclone, and ball mill. This will look like, for example, if I take a feed and the feed, it enters into rod mill. Here I add little amount of water in order to make a slurry, grinding occurs, then the feed it flows into hydrocyclone Here I may add also water if it is required. So, this hydrocyclone divides the feed into two products. One is the undersize and another is the oversize. Now, normally in the hydrocyclone, the oversize it is a useful product and this oversize is sent for concentration operations. This says that means in the oversize we have attained the mineral in the liberated stage and that can go for further concentrating operation, whereas the undersize has a size bigger than the required. So, what is done? This undersize is fed into a ball mill, and the product of the ball mill it can go further to the hydrocyclone. That is what the direction. So, this entire thing is called a circuit of milling. You are required to analyze this circuit. That means, you are required to know what is the amount of water that is flowing, what is the amount of solid that is being flowing, and so on. Or another circuit which consists of only ball mill, you have the feed, one can directly go into the ball mill. Here water is added, then it goes to hydrocyclone, and as such the hydrocyclone you have undersize and you have oversize. So, oversize is for concentration operation and undersize can further go for the further milling operation. This is called the so called a circuit or the milling circuit. Now, in this connection I have to say something more. For example, in case of wet milling, you may be why wet milling is done, there are advantages of wet milling. One advantage is less power requirement, then reduce pollution, because now the fines will not be flying out of the vessel and because of water. So, now this analysis of the circuit is important and that we will do in the material balance. Now, for further reading, if you want to go further, I give you a few reference. So, that first you can go through in the book of A. Taggart, they are the reference where you should update Taggart, elements of ore dressing, Riley, New York 1951, or you can also do another which is the Newton, extractive metallurgy, so John Wiley, New York 1959. However, there are what should I say, there are several books on ore dressing. You can consult any book for updating these particular things or for knowing more about the technological details of the milling operation. Now, once the output of the liberation technology, which is oversized, we have gotten the surety that now the mineral is liberated. Now, we want to concentrate it. So, the next are the concentration technologies. Concentration technologies. Now, as the objective is very clear, here what we want? We want to separate the valuable mineral from the gangue mineral, that is what our objective. So, what we have? We have now a milling product, we have the oversize of milling product, and milling product, what is this milling product? Is a mixture of different size, shape and with different proportions, of minerals of, let me say, of both valuable plus non-valuable mineral, or let us call gangue mineral. Now, we have gotten this mixture. It is a mixture of different size or different shape. That means, there are particles with different size, different shape and their different proportion of both valuable and a gangue mineral. With this I mean, suppose if I have a feed for the concentrating operation, say this I will denote for, say this I will denote the so called gangue mineral, and this I will denote the valuable mineral. So, this is a valuable mineral and this is a gangue mineral. So, the feed will consist of in between these two minerals. That means, you may have a feed which may consist of fully liberated mineral, or you may have partially, you may still have this thing, you may still have this thing. So, this portion is gangue, this portion is mineral. So, what I wanted to say from here, that in the feed which you have gotten from the milling operation, it contains particles with different sizes, with different shape and different proportion of mineral. Now, here it is very important to know that in the liberation technologies, you are say producing particles containing minerals. That is an important, and when you say you are producing particles containing mineral, that means there are particles which are fully mineral, there are particles which are different proportions of mineral. So, with this what I mean to say is that you have to now develop the concentration technologies to develop the particles containing mineral. Now, here you should also note from here that in this mixture we have variation in density. We have variation in density of particles, in density of particles. We have variation in density of particle. What does it mean? Say if we have, it is clear that density of mineral particle, pure mineral particle, that means this type of particle is definitely greater than density of gangue mineral. That means this. Now, in between these two, with different particles with different proportion of mineral will have different density. So, that is a key point for developing the concentration technologies. So, now what we have to do? We have to separate a valuable mineral from the gangue mineral. So, the concentration methods essentially most of the concentration method they are based on density. So, I will list down all the methods. Say first method is based on appearance. Well, if we can do this a physical, if you know the appearance of mineral, they are being sorted out. Another based on the density, where most of the separation is done based on the density, because the density of the mineral is larger as compared to density of the gangue, and density of the particles in between mineral and gangue, one can select the density of the medium, so that separation could be achieved. Another method very popularly done is surface modification. Surface modification. Now, just to give you a little bit idea of various methods, the density methods, they are called gravity concentration methods. They are called gravity concentration method, and in gravity concentration method we have one which is called heavy media separation. Heavy media separation, that is, you select the medium of some density, so that the particle containing minerals can be floated or can be sink or can be float depending on the density of the medium. Another method is called classifier, where air can be used as a medium or water can be used as a medium, and where the velocity of fall of particle is used as a separation, and that is different in air, different in water. So, accordingly you have pneumatic classifier or you have hydro classifier. In hydro classifier you use water as a medium, in pneumatic classifier air is used as a medium, and the difference in density is the key concept of achieving separation of the mineral. Third technology is separation in a particle bed. Separation in a particle bed. And the most important technology here is jigging. And the last one is thin film flowing. Thin film flowing, which is called tabling. Now, the surface modification, that means you modify the surface of the mineral. You know, you are not chemically affecting the mineral, you are modifying the surface of the mineral, so that it becomes hydrophobic or hydrophilic. So, that means, and this method is called flotation. This method is called flotation. Now, the principle is the density difference between the particle containing minerals and the medium which is being used. Now, the objective of all these concentrating technologies is to separate the feed. That means, you separate the feed into three products. One is the concentrate, and in the concentrate the percent valuable mineral is supposed to be high. That is why you call concentrate, and this concentrate goes for plant for extraction of the metal. Now, this concentrate is of high grade and it can be used for further processing to get the metal. Another say product which is from the feed, which is called middling. And third product is tailing. Tailing is purely waste. It contains most of the gangue minerals. Middling, it may contain concentrate as well as tailing. So, what is being done? The middling is further treated, so that some portion may go to concentrate and another portion go to tailing. So, normally the output of a plant, that means plant output it consists of feed is separated into concentrate and tailing. This is the output of a plant, that means feed is separated either as concentrate or as tailing, and concentrate, this concentrate is dried or in wet condition and sent for metal extraction while tailing is a waste and it is it dumped or for the waste treatment or whatever you want to know, you can do it. Now, here you know the one of the most important thing that you should know is the recovery and grade. Recovery and grade. Recovery of particles containing valuable minerals, or let me put recovery of a valuable mineral can be 100%, but the metal grade will not be 100%, it will belong to the metal grade of a pure mineral. So, that means, let me illustrate by an example. If I take an example where I take a feed has say 1000 kg, and in 1000 kg I have 500 kg chalcopyrite, 200 kg Fe2O3, plus 200 kg, let us take SiO2, and 100 kg, let us take is Al2O3. Now, I have got now feed say concentrate. I produce a concentrate now which has also 1000 kg, in which 500 kg CuFeS2 plus 200 kg Fe2O3 plus 200 kg SiO2 plus 100 kg Al2O3. What I have done? I have done nothing. I have taken a feed and said that it is a concentrate and told that I have recovered 100%. No doubt, the valuable mineral in the feed was chalcopyrite, CuFeS. So, no doubt you have recovered all the valuable mineral in the concentrate. But now, what is the grade of this concentrate? The grade of the concentrate is very, very low, because the gangue minerals are as it is as they were in the feed. If the feed has some X is the metal grade, then concentrate also has the X as a metal grade, because you have not removed at all the gangue minerals. So, therefore, the recovery and grade, they are important. Now, if you want to see how they vary, the variation it goes something like this. Say if I take here recovery, which could be for example 0 to 100 in percent, and I take here grade. For 0% recovery, I have this is the value of the grade, and this value correspond to grade of a pure mineral. Grade of a pure mineral. For example, copper grade in CuFeS2 is 34.7%. So, that point is this. Now, you can't go beyond this. The metal grade cannot be more than 34.7%. So, you see the metal grade can never reach a 100 value. It will depend upon the composition of the compound and their stoichiometric values. So, remember grade can never be 100. So, here now if I increase the recovery, what will happen? I will go, the grade will decrease and ultimately I will get at 100% recovery, this will be my grade. So, that is how the relation between grade and recovery it has. So, that means the recovery and grade, a recovery can be 100% in that I do nothing, that is entire feed I divert to the concentrate, but then the grade is very important because we want to produce metal from the concentrate. This is the one. Number two important thing is that for all gravity concentration operation, it is the velocity of the particle that is very, very important. Now, if I consider for example, a particle, if I consider a particle which is falling, so it experiences this, these are the three forces. This is due to weight F w and this is a sort of a buoyancy force. See, buoyancy force, and this is a so called drag force. This you must have experienced if you take a particle and dip in water, because of its weight it sinks, and if the upward forces they equalize the downward forces, then it is stable, otherwise it will move. So, if you do the force balance, then we say that F s plus F k, that is equal to F w. If I substitute the value, I consider a spherical particle, then 4 by 3 pi r cube rho into g plus this is the drag force, this is the viscosity V t. I will tell you what is V t, that will be equal to 4 by 3 pi r cube density of the solid into g. So, if I solve this, then I will get V t, that is equal to d square rho solid minus rho into g upon 18 mu. So, V t is called terminal velocity. V t is called terminal velocity, and this terminal velocity is very important in case of gravity concentration operation. However, this terminal velocity we have determined for the Reynolds number to be very, very less than 1, even less than 0.1. However, for larger Reynolds number, the turbulent forces also come into the picture, and accordingly the value of velocity is to be determined. But what I wanted to say for here, that for the gravity concentration operation, let me put it this nu, that is the viscosity. So, let me say this is the viscosity, rho s is the density of solid, and rho density of water, density of water. So, what I wanted to derive from here is that the V t is proportional to d square. See that larger is the size of the particle, better, higher is the velocity or higher is the terminal velocity. So, you can plot up easily. Also, it is proportional to difference in rho s minus rho. Also, you see it is also say inversely proportional to viscosity of the fluid. It is also inversely proportional to 1 upon viscosity. So, all these three factors have to be optimized in order to produce a concentrate from the milled product. Now, I think there are frequently some asked questions would be there. So, let us see some of the questions.
Sir, can you please explain the difference between ore and mineral?
Now, this difference is very commonly asked, and many a times some students they get confusion. So, let me tell you very clearly that an ore is an aggregate of minerals. That means, it contains valuable mineral as well as gangue mineral, whereas a mineral is an inorganic compound in which the elements are combined in stoichiometric proportions. For example, if I take iron oxide, say Fe2O3, so Fe2O3 is not an ore. It may be confusedly people may say it is an ore. No, it is not an ore, it is a mineral, and in that mineral 2 molecules of iron, they are combined with 1.5 molecules of oxygen, and you get a mineral. But when you call as an ore, then it becomes hematite. Hematite never means it has only Fe2O3, though people say it has only Fe2O3. No, it never means it has only Fe2O3, but when you say hematite, then it has Fe2O3, Al2O3, TiO2, SiO2, alkali, so on. So, in fact, ore is an aggregate of mineral, whereas mineral is an inorganic compound. That is a very important thing, and once you perceive this difference, then you immediately know that the metals, they do not occur in the nature as metal, but they occur in the form of chemical compounds. One. Number two, this mineral or the metal of a mineral, it does not occur as a pure mineral, but it occurs along with the several other minerals. Therefore, the technologies are important.
Sir, what is a particulate?
Well, I think I have not explained this, because say when you take a lumpy ore from the mines, you crush it. After crushing, it undergoes to milling operation, and the milling operation, that is the product which is there, the milled product, is in fact called a particulate. So, essentially I can write down the definition, say a particulate is a mixture of particles, of different size, shape and different proportion of minerals, and different proportion of mineral. So, when you say a particulate, in fact, the milled product which is subjected to concentration technologies for recovering the valuable mineral, that feed you can call as a particulate. Now, that means you have in that particulate, there are particles of different sizes, shapes and different proportion of mineral. Now, also remember, we never say we never separate the particles, we never separate the mineral, we separate particles containing mineral. They are the two different things. We separate particle containing minerals, that means a particle may have full mineral or it may have partially liberated mineral. That means, a concentrate, you should not think that it has only mineral, but it has valuable mineral as well as gangue also, because you are concentrating particle containing minerals, and a particulate has different sizes with different proportion of mineral. So, in the concentrate their gangue will also be present, though its percentage is very small, but it will present. So, that is what a difference, and that is what a particulate means.
Sir, can you give some examples of metals that are extracted by hydrometallurgical routes?
Now, there are several metals which are extracted by hydrometallurgical route. Now, typically the hydrometallurgical extraction route is employed for lean grade ores. For high grade ores, one does pyrometallurgical route, because pyrometallurgical technique can produce very large amount of metal compared to hydrometallurgy. So, for lean grade ores, one uses the hydrometallurgical technique. I can give you example, for example, copper. For copper, the unit processes are roasting, because in all hydrometallurgical operations, sulphide is first of all converted to oxide or sulphates, because in hydrometallurgical operation also you have to recover the metal and gangue you have to separate. So, for recovery of the metal, you have to find a solvent which can recover the metal in the solution form. So, sulphides are normally not leachable. So, first of all it is converted to oxide or sulphate depending upon the type of ore. So, for copper, roasting, then followed by leaching, followed by cementation or hydrogen reduction, whichever is that, and plus electrolytic refining. For electrolytic refining. For aluminum, it is because aluminum you have bauxite which is oxide ore. So, you have leaching plus electrolysis. Similarly, for example, magnesium, you again follow the route leaching plus electrolysis. So, in fact, in hydrometallurgy also sometimes the roasting is used in order to convert sulphide into oxide or into sulphate, because sulphate and oxide can be leachable. So, that the metal can be brought in the form of solution, and then you can adopt the separating technology. So, these are the, there could be several examples. For example, zinc, it can also be done by way of hydrometallurgy, nickel by way of hydrometallurgy, again roasting, leaching, and these are the separating technologies.
So, is there any difference between slurry and pulp?
Well, in all mineral processing operations, these terminologies are interchangeably used. In fact, slurry and pulp, they convey the same meaning. You take solid and dissolve in water. You can call it a slurry or you can call it as a pulp also. But pulp, I think it is coming from sugar industry. I do not know from where the pulp is coming, but well, both are interchangeably used as a pulp and slurry, and both are a mixture of, in mineral processing, the solid and water.
So, please explain once again the separation of feed into products.
Well, here when you say employ size reduction technology and concentration technology. Now, in case of size reduction technology, the feed has undersize and oversize. The feed separates into undersize and oversize, and when you perform screening utilizing sieve, then undersize is one which is passing, that is sent for further operation, and oversize which is sent for further size reduction operation. But when hydrocyclone is used for separation, in hydrocyclone, because of the way in which separation occurs, the overflow is useful and underflow is sent for grinding operation. That is an important thing. Now, you recall in the ball milling circuit, the overflow was sent for the concentration operation and the underflow or the undersize were sent back for the milling operation. But if you perform separation by using sieve, then it is other way around. So, that point is important. Now, for concentration technology, the feed, it normally separates into three products that I have said, which is a concentrate, you have middling and you have tailing. Now, middling you can think of कोई बीच का चीज है, बीच का between concentrate and tailing, that is the middling is. So, middling is rather further processed. So, it either portion goes to concentrate or portion goes to middling. So, in fact, the plant output, in the plant output it has only concentrate and tailing. Concentrate goes for plant extraction and tailing goes for waste.
Thank you, sir.